This is a testing video for my computer science NEA, which is a Tetris AI that learns to play using a genetic algorithm. So in this video, I'm just going to go through objectives that I set out at the start of the project. We're going to compare with the final project, and we're going to see whether these objectives have been satisfied. Objectives, I split them into the Tetris objectives, and that just means that these are specific to how the game's implemented. Then we have AI objectives, which are specific to how the AI should work, and cups, things like that. So we're going to go through each objective. First, we're going to go through the Tetris ones, compare with the implementations, and we're going to go through the AI specific ones. So another thing I want to mention is that the Tetris file is split, so the code is actually Tetris.py is the human playable version, and this Tetris AI.py is the one that's actually used for training. There's a few differences between the code that we'll point out during the testing, but I kept this one because I had to test, and I suppose just for fun to have it to play. Yes, one more thing, the project was certainly helped with a lot of research and reading from other sources, which I have put in the documentation. So also in the GitHub page, they're just in the README. So those are the sources I used. I did not think of everything just from scratch on my own. So that's another disclaimer there. And I think let's get started. So starting here with the Tetris objectives, the game should be playable, and the player should carry out any moves without the game crashing abruptly. The game should have error catching capability and should output relevant error messages for the user. Player should be able to pause the game, hard drop, carry out translational and rotational moves. Player should be shown help instructions for controls. The game should follow the indispensable Tetris guidelines. These are just guidelines that are up on the internet, set out by some people that think this is how Tetris implementation should work, and that's how it should look. So I tried to follow most of them and derived some guidelines here that I set out as objectives. So playfield should be 10 cells wide and 20 cells tall. The game should allow for natural rotation of a tetromino piece. Piece preview should be available. Player should be able to hold a piece. Hard drop should be an option. The colors of the tetrominos should be as follows, and these will compare during testing. Pieces are generated with a 7-bug algorithm, which is explained in the documentation and is implemented in the code. The game must include the version of the Krobeniki music, and the game is over when the piece is spawned overlapping at least one block above the playable field. Okay, so let's just start the Tetris file here, and this is what we have. So I will put this here. So we can see first of all that the Z piece is red, as it should be. The I piece is light blue, as it should. Again, we get the S piece and I piece again. Okay. Oh wow, S piece again. That's fine. And now we get the T piece, which should be magenta, so that's fine. The yellow should be for the O piece, which has been satisfied. O piece again, we get the S piece should be green, which is fine. And again, we get the Z piece, which we've already seen is red. And now the L piece should be orange, so that's fine. We get the S piece again. T piece should be magenta, yellow for all. Yes, the J piece finally is dark blue. So I think we have managed to do all of those. And whilst I'm playing here, you can see that I can carry out any translation move I want. So I can go right to the wall. It doesn't just merge and go through the wall. I can hard drop a piece just by pressing tab. And yeah, all pieces seem to be carrying out all the rotations that they should be carrying out. And that seems to be working fine. I've also held a piece there. So whilst I'm holding a piece, I can't hold any more pieces right now. if I unhold the piece that I'm using, I can place it and it works fine. And now I can hold more pieces, I can hard drop, and I can just keep playing as much as I want to. There's help instructions just on the side there. Maybe if you've never played the game, or well, this implementation will be different, so yes, you probably need the controls anyway. So we have help instructions there on the side, and we can actually pause the game if you just want to read those. So now I've paused the game, and it shows a nice paused effect if you look at it vertically. And here are some controls in this specified as they are in this implementation, and just a nice Windows XP background for some nostalgia, I guess. And that's it for the kind of theme of the project of the Tetris, of Tetris, how it's implemented here. So that seems to be fine here. And notice that if I go to the wall, anytime I go to the wall, just put this here and pull up the console, it prints out some messages. So move is invalid. So if I go to the side like that, it says the move is invalid. It doesn't just crash, it tells me what I'm doing wrong. If I press a key that's not actually valid, it says move is invalid, and it doesn't allow me to make the move. And I think that's that, so I will just close this, and then also the game immediately fails or stops there once the piece spawns above the playable region, just as it should. And I think that seems to be it for the Tetris ones. Also the playfield, 10 cells wide, 20 cells tall, was fine. Previews were certainly available. We could see the next piece that was going to get spawned, and it was also spawned correctly. Players were able to hold the piece, so I think all these are done in the implementation. So for the rest of the testing, I will comment out the music for now, and I think that is it for how Tetris should look and how it should work. We had the music, and the game ends as it should. So that seems to be kind of outlining how the Tetris should work, how it should run. I think we have attained. So I will now move on to the AI objectives. So these are, since this is an AI project, I just set out some objectives. For example, maximum score we should get to the end of the project, and how the AI should play, and other things like data visualization tools. So I'm going to go through them one at a time and see whether we have managed to satisfy those objectives. So starting here from the first one, AI should achieve a score of at least 200,000 by the end of the project. Let's move this to the side a bit. Under a condition that it has trained for only 10 generations. There is no cap on the number of pieces dealt, so the agent, any given agent can play for as long as it wants to. It's not like we're dealing the same number of pieces for each agent. The AI should be reasonably good at the game, should make choices most human players would, and sub-objective here is that the agent should demonstrate good Tetris play through emulating non-human strategies. The agent should demonstrate good Tetris play by placing pieces in reasonable positions, given the situation of the game. An example I gave here is that it shouldn't try to make a move that would basically make it lose, or make the structure taller if they're almost going to lose the game. Data visualization tools should be used to graph AI progress, so this all uses matplotlib. And the AI should accurately follow ideas behind genetic algorithms. And lastly, AI should have useful AI testing features. For example, it should save populations after a given number of generations, and programs should offer an option to carry out ablation, and you should be able to load populations at a later time. So I've added a timed sleep function, just so it's not too fast, so that we can actually see the moves it's making. I've also added a function here to show us the best move of the agent, so that we know it's actually placing it in the right position, as opposed to this, because we'll have to try to spot it with our eyes, which is quite daunting. So I'm just going to start this. When this starts, the first thing we'll see is a ablation list, and what that is just a list of all the heuristics and an index for that heuristic. So that means that we can just type in a number at the end here. So for example, 0 will ablate the deepest wall heuristic. Then I can type in comma separated values as well. We're going to look at that later, but for now we just want to load a population. We are going to load from the 8th epoch, and the window should pop up, and here we go. So the gray piece just shows where the agent wants to place the piece, and then then we can compare and see whether that's where the actual piece ends up. And I think that's what's happening here. On the side here is just a counter, so each small is just a kind of visual representation of how far we are in a generation of training. Each small box represents a genome. There's a thousand of them right now. The green box just shows this is the current genome we're on. So a few differences with this one is there's no gravity. So the piece is looked at, and then best moves is found, and then the piece will be placed. And in terms of play, it has not lost the game yet, so we will be able to see hopefully later and try to observe its strategy. One strategy that I have observed is what I've decided to call the eyepiece strategy. So it tries to build its structure as tall as possible, and then waits for builds a certain column and just waits for the eyepiece. In terms of other forms of play, it's I'd say playing quite well, trying to clear as many lines as it can, whilst also balancing that with trying to build a tall enough structure so that it can clear many lines at once to make Tetrises. So like what's it trying to do right now? So that column could not get the eyepiece fast enough, decided let's just get rid of the tall structure for now and try again later. But I would say in terms of play, demonstrating quite good play here. Places the eyepiece there at the end to try to clear many lines, and another good eyepiece placement there. And I would say I'm quite happy, very happy actually with this play style. So I think it's trying to build that first column, but I suppose it couldn't get the eyepiece fast enough, and then it just keeps playing, and yeah, this seems to be working fine in terms of good Tetris play. What I've found is normally what you want to do is leave this to stabilize, quote unquote, because this is just the first few genomes in the population. We might not be seeing the best, the very best ones that hit the maximum score of 5 million, something like that. Those usually play for much longer and implement better strategy even than this might be implementing. But generally it's playing quite well, playing good Tetris in general. So we've tested that loading population works. Now I will stop this and explain something. You might have noticed that when I loaded the population at this stage, it did this crossover and mutation. So why is it doing that? That's because the way I've set it up to work is it will pick depict our population. The thing that's actually in the file is just there's a certain file that stores all the weight matrices of each genome, of each neural network, and there's another file from the same epoch that stores all fitnesses. And what happens is that it assigns each weight matrix to each genome in a new population, and then carries out crossover and mutation on that population. So that way the system is starting from the population that I loaded. So that's why that's there. And then the rest seems to be working quite well. So we'll remove this for now, and I'll probably remove the time.step as well. So moving on to the other tests here. We'll look at data visualization later. Perhaps I could take some time to explain some of the concepts behind genetic algorithms that I used, try to compare them with the code. So I will do that. I will need to load the file in which this is programmed, and here's the code. So I'm going to explain the main concepts here. So at this stage we're doing a crossover, and that involves picking the best two parents from a population and trying to create a child which shares weights from each of the parents in some way. So at this stage, if it's just a weighted sum at this stage, so you can see that we choose two parents A and B, and A and B are actually from the region of the best genomes. So we do a weighted sum of each of the fitnesses and the weight matrices to then come up with the child. However, if both of them are 0, we'll get a division by 0 error. So that's if we're at the very beginning of training. So that's why I had to add this, where it just does everything manually. So it goes through each child matrix and places with 50% probability the weight, the same kind of weight from the parent A or parent B. Yeah. So another feature we should test is saving a population after a set number of epochs. We should be able to load these populations, which we have looked at, and the program should offer an option to create ablation tests. So we're going to test that right now. So if you want to see saving, waiting for it to train 1,000 genomes would probably take a long time. So what I'm going to do is I'm going to have it train for just one epoch, and we'll set this checkpoint to 1, so that it can save that epoch. And what we're going to do here is set this to train, let's say 10 genomes, and let's see how that works out. Here is a file that contains all kind of the populations, and you can see in here that I already have saved all the populations that I just picked. So epoch 2, the population, these are just the weight matrices, and this is the list of fitnesses all the way to the 10th epoch. So we can come back and check in here and see whether that has been saved. So let's just run this. And we're just not going to load any population. So count has reduced to just 10, and that is training. So hopefully when it's done training, it saves that population for us. So we can see that here we just have a comment that says that the population was successfully saved. We print out all the data to the file, to the console rather, just in case matplotlib does not work in terms of passing the data in. You have to manually create an object to pass all the data in. So here we just have the average score attained 64, which makes sense. It's just a random population trained. Yeah, we can't really measure the time, just probably less than a minute. And let's just go check on the epochs. So we can see right there, it saves the fitness and the population. The fitness list is actually using NumPy, but it's basically Pico with NumPy, so it's basically the same thing. And then we have the population right there. Alright, so I will delete these. So now we know that works. We can save a population and we can load a saved population. So that's fine. Okay. The next thing we could test here is ablation tests. Okay. Ablation tests are a series of tests we can carry out in removing some heuristics and seeing whether and try to compare performance. So it's just a way of comparing heuristics with each other, seeing which are more important heuristics, and basically are these heuristics actually making the agent better. So I have a certain result I will show later with the graphs of these last 4 heuristics ablated. I have some graphs to show, but generally I'm just going to test and see that, and just show that we can carry out any amount of ablation we want to. So we're still training just 1 epoch and just 10 genomes. So I can type in a single number, so let's start with that test, and it immediately just starts, and that seems to work. So it's the goal of the test really is to just show that it still works fine, which it does, and then that finishes training and prints out the data that we need with a much lower average score. But that's probably not a very fair comparison. We will see a much more fairer, trained over 10 epochs with the graphs later on. So that's ablation. Let's now try it with again, these were saved, so that's more confirmation that that works. I'll probably remove it now. Then let's now try testing ablation with multiple heuristics. And see how that works. So let's say 0, 1, 2, 5, 7. So it's just starting to train now. It is interesting, still clearing lines. But here we are. It's just doesn't seem to be playing very well, and an average score of 36, and that's ablation. So ablation seems to be working fine here. So we can carry out ablation tests, and I'll show you some results that I trained earlier on. We're going to look at that later in the video. Okay. More objectives here that going through, see if I've missed out anything. We're going to look at data visualization and graphs whilst comparing performance or evaluating performance. Okay, I think that's that. Let's move on now to the graphs and look at how that is playing. So that's pretty full test there for how the program works and how it can be used to carry out comparisons between agents and ablation and things like that. In terms of graphs, here's what we have. So I will probably focus on this now. So this is just directly from the documentation. Some of these are on the GitHub page as well, but we're going to go through everything here. Sorry about that. So, first of all, results with no ablation. So this graph just shows average fitness of all genomes against epochs trained over, and we can see very steep increase in fitness of the genome, hitting a peak at about 1.38, and then dropping. So these fluctuations are common. I think it's due to mutation, because I don't think it's due to the crossover. Because the way it's programmed is it should have an elitism threshold, so that elitism region, and what that means is that the very best, about 20% of the population immediately go to the next population without any crossover, because that might poison them, quote unquote. So I think it's the mutation, because it just mutates the population no matter what. So over time, I suspect maybe 30 epochs of training, we could see it get even higher than this peak, but this is what we have for 10 epochs. Moving on now to the score, we have an average score of close to 1 million by the 9th epoch, and that drop which corresponds with the drop of fitness, which makes sense. This 10 epochs of training took about 2.5 days to train. So I suppose that's a kind of indication that it must be playing well in some ways, because then the games would take longer. The games take longer, and therefore it takes some more time, but it's 1,000 of them, so it's still, in comparison with some of the ablated models that I've done, those take about 20 hours, something like that, less than a day. So that's I suppose a comparison on time of training time is enough to tell us that the ablated models are actually not as good as the average score, as the zero ablation models. So here we have an average score of 900,000, about 950, which has surpassed the targets that we set. So we set 200,000, actually 200,000 maximum. So this is average score. I believe the maximum for this was somewhere about 2 million. So that has been satisfied. Now moving on to some ablation tests. The results I have here are ablations for 5, 6, 7, and 8 ablated. So here we just have a graph of the red maximum fitness per epoch and average fitness. Focusing just on the maximum fitness, or hitting a maximum very, very high fitness. The fitness probably doesn't matter much in terms of Tetris. It's just good to see that the genomes are generally getting better. Then there's just a huge decline there, 7th to 8th epoch. It starts to climb up. I suspect with more training, it would even get higher than the 7th epoch peak. Looking now closer at the average fitness graph, that's the same data. It's just a clearer graph here. Again, we see generally an increase in fitness, which is good. Moving on now to the scores. Again, we see a general increase in maximum score per epoch. Interestingly, 7th epoch on this ablated model hit about 5.7 million in the score, which is quite surprising. Generally, 5 million maximum here is about 4 million. Hits about what seems to be 500,000 by just the 2nd epoch, which is fantastic performance. Looking at the average scores graph more closely here, again, same data. The average is very, very good. An average score of over 1.4 million by the 10th epoch, which is certainly much better than I thought this would perform. But here are the results. So now, capping up on the video, the code is on the GitHub. The link is in the description. And I think this is it. This has been the testing video for my computer science NEA. Thank you for listening.